This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Some students, they nearly complete the project. Which from my perspective, that is okay. However, please do pay more attention to the plagiarism. Okay, so the final project, we will check your similarity and make sure it won't. The work you submit for this subject will cause any other issues in that field. Okay, and if you have any inquiries, please come to me or Niraj during the tutorial, so we can give you maybe give you more detailed feedbacks in regard to the previous two assignments. Okay, then we will start today's lecture, which is Introduction to Econometrics. Well, today we will focus on the cross-sectional regression model. Okay. So what is econometrics? There was some sentence may help you give you guys a general idea about econometrics. So econometrics is, simply speaking, it's just a quantitative analysis of actual economic phenomena. So that means in the research, sometimes we don't exactly know what's the theory behind the economic behaviors. However, we can collect some observation of the economic activities. Then we run like the quantitative analysis, or we use econometric methods to generate the generalized model, or maybe a theoretical model, to explain the theory or the rules behind the practice, behind the practical economic activities. And that's the definition of econometrics, which means economic measurement is a quantitative measurement and analysis of actual economic phenomena. So that is all we can say. Econometrics is kind of a theory of applied economy. So it's we build, or we deliver our research built on some theory that we have already know, and then we use the practical data to test whether the theory is correct, or whether we use practical data to improve the existing theory or rules in the economic field. So that's why normally we regard the econometrics as the bridge between the theoretical economic world and the real economic world. So how can we use econometrics in the research? First, we can use them to describing economic reality. For example, hedonic model for house prices. So we know the house prices are influenced or determined by certain factors or by certain elements. Then we can collect the real data and put them in and use the econometrics model to test whether the theory or whether the theoretic model is correct or not. And it can test the hypothesis about economic theory. So that's, for example, then it becomes a little bit more specified. So, for example, not all the character of horses, but we will specifically or particularly want to explore whether the distance to train station will influence the house price. Then we will use the econometrics model to test or to quantify the effects of distance. And then, based on this estimated or the specified model, we can forecast the future economic activity, or we can forecast or simulate other similar economic activities. For example, if we estimate a model year, and then we can use the model to predict a house, or maybe 3-bedroom house, located within 2 kilometers to the certain train station. So that's what we can use econometrics in our real life or in our research. So that is today's agenda. So today's lecture will mainly cover the 4 components. One, we will have a quick briefing of regression analysis. Then we will look through the process of regression analysis within the SPSS environment. And finally, we will, that's linear regression, and then we will also touch on some other forms of regression models. So first, regression analysis. So regression analysis is a statistical techniques that can be used to explain the movement in the dependent variable as a function of movement in a set of other variables, which usually we call them independent variable or explanatory variable, or in SPSS they always call it a predictors. And the regression model can be expressed like this, that's the dependent variable house price, and then it is a function of maybe bedroom, number of bedroom, distance to the train station. Let's just simplify for the teaching purpose. Of course, it's a function of more factors. That's the theoretic model. And then in econometrics, we are going to specify the parameters, the coefficients of each parameters. Like, for example, in linear regression model, we will say we will assume that the house price equals a constant plus number of bedroom and distance and an error term. So the error term can be regarded like can be divided into 2 components. One is the unsystematic error. So that is, or maybe random error. That the error we cannot avoid or reduce. So, and another component of the error is a systematic error. That is mainly caused by some unobserved factors. So, for example, in this equation or model, we didn't include, for example, number of bathrooms, or maybe the area of land. Then they will all affect the error term. So that's the linear regression, and which is the most widely used regression model in our research analysis or in econometrics analysis. We can find there is a B0. Normally we call it intercept or constant, which is the connection with the line of the line and the y-axis, or the axis of dependent variable. And also we have the coefficients of the parameter or of the variable or independent variable, which shows the slope between the dependent variable against the independent variable. And of course, we have other non-linear regression models. And here's the general steps in regression analysis. First, review the literature. So in this way, we can create or we can develop our theoretical model and identify the parameters, and then we are going to specify the model. So what parameters should be considered, or why they should be considered, and then we raise or we create a hypothesis for the expected coefficients. So, for example, it's like if we are going to estimate the house price and the number of bedrooms, then before we running the model, we should have our own judgment based on the previous literature or based on our experience. We see, okay, maybe there is a positive relationship, okay, or there should be a negative relationship. So that could guide us to test or to adjust the following estimation results. Once we finish all the theoretical preparations, we are going to collect data. And collect data for the dependent variable and the included independent variables. Then we run the model, or we estimate the equation, and we also evaluate or validate the estimated equation. Finally, and then we probably will rerun the model, or maybe we will recollect some data, or maybe we improve the theory or improve the hypothesis, and eventually we will have our final results, and we document and present or interpret those documents. That's the 6 steps are the normal procedures which we can adopt or adapt to for our regression analysis. And today's lecture will focus on this step, just evaluate and estimate and evaluate the equation. And there are many softwares which can be used to run the econometric model or to deliver the regression model. For example, SPSS, which we are going to introduce, and also we can run them in the Excel software. And however, for econometrics, Stata, and also eViews, these are the two softwares which are specifically built for econometrics analysis. So in today's lecture, we just assume that we are going to run to estimate how will the house prices in Box Hill be influenced by the distance to the Box Hill train station. And that's the summary or descriptive statistics of all the data we collected from the website. And we can see that's the mean, maximum, minimum, and standard deviation. And then we are going to import the data into the SPSS. Did anyone has anyone used SPSS before? No? Okay, so that is a software which mainly used for social science analysis. I think the full name of SPSS is a statistic package of maybe of social science. Probably that's the full name, and it has massive functions or statistic calculations or package in SPSS. It is a good software. It has a function for cross-sectional data and also for spatial and time series data. But it is good or more functional when we do the cross-sectional data. So if you can open the SPS and then we select new data set and then open, then you will find there are two windows. So unlike the common software, it has two windows. This one I call it maybe operational window, or they call it data editor. So where we can input our data. Here, that's the data view. Input our data here, or manipulate the data, create the graph, or calculate the statistic, or run the regression model in this window. And also, it has another tab or another view in this window, which called variable view. So where you can define the properties or the features of your variables. So this is one window we operate or we run the analysis, and the other window is the output window. So that's all the results of our operation will be displayed in this window, and then we can export or copy, and also save the results of our operations. Okay? So then we will import the data. So we go import Excel and just click on the Excel sheet. Then you can choose the range and also define what's the first row, and then click OK. Then we save it. Then we save the data here. Now we can see all the data are imported into the SPSS. And if we see the data, the variable view, can you see the screen? Is it? Yeah. Maybe I'll just turn off the lights. Is it better? And you can still see my face, right? Okay, that's great. Then here we have the name of the data. We have the several columns. The first column is the name of data, which is automatically taken from your Excel sheet. Okay, I mean the first row of each column in the Excel sheet, and then here that indicates the type of the data. So we have in SPSS. It has many types of data, and you can define the data. I mean, the SPSS can automatically recognize the type of data based on the information in the Excel sheet. However, if you find there was some data is not correct, you can add it by click the tab beside the cell, and then you can redefine the type of the data, where we can find out all those data are numeric, unless this one, parking, because in parking we use the NA to represent the missing value. However, I mean, the SPSS cannot automatically recognize this unless we tell them. So in that case, we have to change this. I mean, the string means text data. So we have to change the type of data to numeric. So that's the type of data, because if we are going to run the regression model, they can only run the regression model based on the numerical data, not the string data or the textual data. And also here it indicates the width of the data, like how long your data is, and it is also automatically recognized based on the data in the Excel sheet. And if you know there was some mistake, maybe you can also revise the width of the data, and also that's the decimal, and this one label, which is very important. I think it's very important for the output, because if you do not give them a name, then in your output the SPSS will give you like the generalized name, like variable 1 or constant or something. I mean, if you can revise or give them a label, then it can be shown in the output, and that can be better recognized, especially you are dealing with a lot of variables. And then that's in the column, in the value column, that's the value. So it may not so important for this subject. However, if we are doing some qualitative research, it is very important. It's kind of a coding process. It's like, for example, like the dummy variable. So, for example, in the parking, we define value 1 is there is a park, right? Is a parking or garage. Or maybe we just simply say yes. Oh, sorry. Click on the wrong one. So, for example, parking. I mean, the data in parking is actually has been coded before, because we define if there is a parking space or there is a garage, we give them a value of 1. So it's like parking. And if there is no, we will say there's no parking. So if then it's kind of we code the data, or we code the information, and once we done that, if we go back to the data view, and then we click on this function. See, you can see the parking is not right. So the number of parking. So anyway, just an example, just the wrong data I'm using. So it's like once we give we code the data, it will be automatically shown in your data view. And then that's the column for missing value. And also you can use the transform and replace missing value by selecting the data you're going to transfer, and give them a way how to replace the missing values. And also this shows the layout, and also that's the measure. So it's like how you want the SPSS measure your data. So there are 3 types of measurement. One is a skew. Skew means just like the number, or the ordinal the number. And the second one is the ordinal. So the ordinal also is more applied to the quantitative, or for the degree of data, like for example, how do you feel like this subject? Okay, maybe your answer will be like dislike, strongly dislike, and then we give each of your expression a number. So like a 3 to 1, and the number in the number under the ordinary, it has an order. It has a order. It's like 2 is more than 1, or 2 is higher than 1. And the third one is a nominal measurement. That means although we code the data or information by certain numbers, but the numbers doesn't show the hierarchy or show the degrees or show the order. For example, female is 1, or maybe we can code the gender as female is 1 and male is 2. And in that case, we cannot say. The 1 and 2 is a nominal skew. We cannot see 2 is better than 1, right? So that's typically gender bias on the grade women, right? And we cannot say maybe is 1 is less than 2 because they don't have that meaning of degree. They just show the different concept or different content. So that pretty much about the data or the operational window. And then we will see all the output in the output window, which is here. So now you can see it recognize our activities in the SPSS. What we have done so far is indicates we have import Excel sheet. Then we are going to estimate the regression model in the SPSS. And before we do that, I'll just give you a quick introduction to the estimation method. So, which is ordinary least square estimation or estimator. And we use the simple linear regression as an example. So, for example, our pure theoretical model or equation is Pi equals beta 0 plus beta 1 number of bedroom I and epsilon I. So here the subscript I indicates each piece of case or each piece of sample. Okay, in our in the example we have 236 samples or 36 observations. Then therefore the I equals 1 to 3, 4 and up to 236. So that indicates the single or individual sample. And then beta 0, as we mentioned, that's the intercept, and that's the coefficient, relationship coefficient of number of bedroom, and then epsilon in the error term. If we run the regression model, we can find that is Pi hat. Is that what you call that? The height. That's we see the letter with the height on top. It indicated the estimated value. So here, that's the real value. Okay, so that's the value we collect from either the website or from the database. That's the real sold price. And this one, the P height, or that is the estimated value, which is generated by the software, or here is generated by the SPSS based on the model or based on the equation. And then we got the estimated intercept, estimated coefficients. So how does the OLS estimate or generate those coefficients or estimate the model? it estimated by minimizing the sum of error squares. So it's like they try maybe different beta 0 or beta 1, and then they will generate different I, and then different sets of I, and then they will choose the estimator which generated the lowest value of the sum of error squared. Okay, that's pretty much the process how the model is regressed or how the model is estimated. So here this choose beta I to minimize and in mathematics we can manually calculate the beta 0 and the beta 1. However, that's just for the simple linear regression when the parameter is 1. Otherwise it's too hard. So normally what they do is first they calculate the beta 1 or the coefficient based on this function. Actually, the numerator here is kind of the covariance between the number of bedroom and the house price, and then it divided by the variance. So if you see the function here, that's the variance of number of bedroom. Then we can calculate the estimated beta 1 or the estimated coefficient of number of bedroom. And then based on that, we can calculate the beta 0, where is the estimated intercept by using this function. So that's the street height. That's indicates the average value of price, and that's the average value of number of bedroom. So from here we can see the intercept indicated the differences between the average value. So now let's see how we can do this in SPSS. Then you will find it is very simple. We just simply go to Analyze and then Regression. Then we choose the Linear Regression. So here we will select the transaction value as our independent variable. And then we choose the bedroom as our independent variable. And then we can click OK. Now it gives us the estimation here, and we start with certain analysis or certain tests, which is in this case the pay or the house price equals 52,000 plus 90 with the number of bedroom and with little errors. So that's then we can estimate the model. So why we use the OLS? That's because that's the easiest way, okay? Comparing other estimation methods. However, I mean because it is the easiest method for estimation, it has the strongest assumption, where it's like we assume all the data, all the value of the data are fixed. So it's like we assume the data we input into the estimation can represent the whole population, and also we assume the constant, the variance of the error data is constant, and also we assume that the error, the estimated error is independent. So it's like this error is not correlated with the independent variable, nor the dependent variable. That means that, in other words, the assumption is that the current model has include all the possible parameters or all the possible independent variables. So that's the assumption we made by using the OLS, or ordinary least square estimation. Okay, that's the property of this. Shall we move on? Yeah, maybe we move on. So we can see estimate the regression is very easy. However, the data analysis is not the eventual target or eventual step in the data analysis, because afterwards we estimate the model, we have validate the model, which is I think more important in the process. We have to see whether the model is correct, whether the model is accurate, etc. And so therefore we have to do some validation, or we have to do some test against the estimated model. Before we process, we just spend some time to know some terminologies. One is the total sum squares, which is, so maybe it is a little bit easier to do this way. Okay. So suppose we estimate the model like y height equals beta height, beta 1 height times x. Okay, and this line is the estimated linear model represent. And here that's the average or the mean of y and x respectively. First, we have one terminology called total sum of squares, so which is calculated by the yi. What is yi mean? So that's the real value of our data, or the real value of the dependent variable, and it minus the average value of the dependent variable. So that indicates how far is the real value move away from the average or from the mean. Okay, so that's one thing. And we have another distance, or we have another sum of squares, which called explained sum of squares, so ESS. So here we can see that is y hat. So that means it records how far is the estimated y, or the estimated value of dependent variable move away from the average. Why we call it is explained sum? Because the estimated value can be regarded as being explained by the model. Okay, so that is the thing we know. Okay, so for example, that's the real thing, and that is the thing, or that is the component we have already know by estimate the model, or by the model, or explained by the model. The third one is the residual sum of square. So we can tell from the name that is the distance or the error or the components that cannot be explained. That we call the residue. Okay, that is the error. That means the difference between the real value and the estimated value. Okay, and you know that's the sum of squares. So it's like it's not a single value. It's like we have a series of this type of value, and then we square them first, and then sum them together to get TSS or ESS or RSS. So then we are going to do a series of tests based on those values. The first one, or maybe we do, is analysis of variance. So normally we call it an ANOVA, right? So and the most important test in the analysis of variance is the F-test. So that's the function of F-test. Okay, probably that's the explained sum of square divided by the residue sum of square. So it's like it just indicates the proportion between the explained, the something we can explain against the something we cannot explain it. So that in that way, the high value indicates the better results of the estimation. So that is the validation we did for the model as a whole. Okay. So in this F-test, we have a null hypothesis, which is in this case we assume that this model produces the equal fit as this model, where the independent variable is not included, and then the alternative hypothesis is that this one does not, or this one produce worse, or in other words, is that we should include this parameter, or we should include this independent variable. Then we can calculate the F, and then we compare the F with its critical value. I mean, there is a table which is called F distribution table, and it lists all the critical value for different level of significance. So normally, if the value is higher than 4.32, is that we reject it at 5% significance, and if it is higher than 2.96, that means we reject the null hypothesis at 10% significant. Okay, and then we can probably we don't have to go back the SPSS. So then we can find there in our output window, we can find there is one table, which called ANOVA, and it indicates all the values of the squares, right? And then it shows the value of the f-test, and also it shows the p-value or the significance in here. So that's the p-value, which indicates the probability of the distribution of the value or of the f-test value. So in that case, we say, okay, the proportion of the probability is less than 0.000 something. Okay, so it's very tiny probability. That in that case we reject the null hypothesis, and we conclude we should include all the models should include some independent variables. And also the DF means degree of freedoms, which is typically statistical terminology, indicates normally can be calculated by n minus k minus 1. So n is the number of observations, k is the number of independent variable. Okay. And on top of f-test, we also have another test or maybe another value to tell the good or bad of an estimation, which is R squared. So here you can find R squared can be calculated in this way. And again, it shows that's the 1 minus the residue sum of square divided by the total sum of squares. So in that case, the higher value of R square indicate the better fit of the estimated model. And also we have an adjusted R square for if the number of sample is not that big. We can calculate the adjusted R square in this by this equation. And also in the SPSS output window, we have a table for which called model summary. It indicates the value of the R square. Okay, probably we can have a break, and then we can come back in 11:05. Okay.
It's more accurate than the. So it's like, yeah, but the compare with if you have hundred or thousand. So it's like
要求你去专业的，然后你去写配套。
Okay, so the F test and the R square, these two values are the test or the indicators to show the fate of the model as a whole. The F test can also be used while you choosing the proper parameters. For example, if you think, okay, there are possible 10 parameters in your model, and you don't know whether you should include them all, probably you can run the f-test several times by excluding one of the indicator and see how the f value changes. If the f value goes down, that means that you probably should not exclude the parameters. And if the f value goes up, probably it indicates that probably you should not include that indicator in your model. So that's the way. Not the way. That's the value we can rely on to specify or to further improve our estimated model. Okay, so just because theoretically you think maybe house price is influenced by bedroom, bathroom, and number of garage, etc. And eventually, in your case, you may find maybe the inclusion of maybe a number of bathroom or number of garage will decrease the value of f-test, and also you find even the estimated coefficient which we are going to describe following is not significant. Then probably you should not include the number of garage in your model, or maybe the number of garage does not influence the house price in the area you observed. So that's the way how you improve or modify your models. Okay, and then R square. So we use the R square and the f-test to validate the model as a whole, and also we should evaluate or validate the coefficients individually. For example, we know we can calculate the standard error of coefficient by using this function. That's the the standard error of coefficient. And then we have a t-test to test whether the beta should equal 0, and alternatively we accept the beta is not 0. So that's kind of a t-test we use. Is like if the t-value was distributed in the blue area, we cannot reject the null hypothesis. So here is 0, and normally we can. Normally it's 0, and you can also specify the value you expect. And if the t-value is distributed in the green area, then we just reject the null hypothesis and accept the value is the coefficient is statistically significant. So for example, we can, the t-test is calculated by this way. Okay, so that's the estimated coefficients, where in the estimated model, the beta hat minus the broader value of the non-hypothesis. Usually there is 1, and divided by the estimated standard error of regression coefficients. And also in the regression model table, in the coefficients table, we have a color which indicates the t-values. So that's the t-value. Actually, that's the value here for tk, okay? So here we have two t-values. One is 7.3, one is 4.2. And also we have the p-value, which is calculated, which indicated the probability of the distribution of this t-value. And it indicates the significance of t-test. So, like if we set up, so in that case, whether we should say this coefficient is significant, it's based on the preset critical level. Normally, I mean, in statistics, normally we adapt 5%. So which means we reject the non-hypothesis if the significance is less than 0.05, where in this case, both of the coefficients are they significant or not? Anyone can guess? We should reject the non-hypothesis. The non-hypothesis is 0. And here we reject the non-hypothesis. That means we accept that the coefficients is not 0, which means they are significant. So that means this one and this one, these two values are significant. So each of the coefficients has, in the estimation, it has two, I think maybe we can say that's two properties or two attributes. One is the value, okay? So it shows the extent of the influence on the dependent value, where in this case, that means the number of bedroom will influence the house price by 90,000 plus. So that's the value of coefficients. And also we have another feature or another property for the coefficients, that is the significance. So whether this one is reliable, is indicated whether this value is reliable. So in this case, because it is significant, then we should say, okay, this is probably right. However, if this value is higher than 0.5 or 0.05 or 0.1, we will say this coefficient, although the coefficient is 98,000, but it is not significant. That means in reality, maybe the number of bedrooms does not influence the house price, although our estimated result is such. Okay, so that's two things we have to look into in the regression, in the estimation results. And then we have not only the model, the coefficient, we also have to validate the residues or the error terms. I mean, as we mentioned, there is a very strong assumption in the OLS that the error is random, they are independent, and also they have the constant variance. And if they do not, I mean, if the error term cannot fulfill the three assumptions, we call this kind of stochastic error terms. I mean, those error terms may caused by wrong function we use, like we assume it is a linear regression. However, it is not, and maybe caused by the omissions. So probably there were other factors or parameters we haven't included in the model, and also some measurement error, and then also the purely random variation. So that is what we assumed. However, in the SPSS, how can we validate the residues? First, we need to generate the error terms. So in generate the error terms, if we just go back the linear regression windows, so you can do this in once, because undo them separately. Just want to show you the steps. However, while you do while you run your estimation, you probably can do it in once. You don't have to do it separately, unless you don't want to test the error. So if we click on the save function, you can choose some additional values or additional data you want to generate it by the estimated model. Like we can choose the predicted values of house prices, like unstandardized or standardized, and also we can choose the residues, standardized and unstandardized. And then we click continue, and then we choose the dependent and the independent variables. Then we click OK. Then you will find there was two records for your regression, right? And you can find the results are the same. However, if you go back to your data or the operational window or the data editor, you can find there were four more new series. One is the PRE1, which is the unstandardized predicted value, and also that's the standardized one, and that's the error for unstandardized. And that's the standardized residue. And you can find for example, if that's the unstandardized predicted value, and that's the unstandardized residue, and that should be equals to the real value minus the predicted value. Then you got the residue. So in this way, you can generate the errors for each piece of sample or each piece of information. So what will we do for the residue? First, we're going to see whether the residue we can run like the analyze descriptive statistics. We can see the the major statistics of the residues. Where is it? Unstandard residue. And you can do this in the Excel sheet if you are more familiar with the Excel sheet, by copy or export those series to Excel sheet, and then you click OK. Then it shows you the descriptive statistics of the residue or of the error terms. You can see what is the minimum, maximum. Sorry, that's the one we produced based on the standard residue, and the mean and the standard deviation, skews, totals. And here roughly we can find the skews is 3.3, while the standard deviation is less than 1. That indicates that is not a normal distribution. It will maybe skew to the right hand side. And also we can run the test of normalities for the residues. If we go back to the standards, to the data editor, and go to analyze, and then we go to explore. We choose the data we want to see, dependent variable list. Yeah, then we choose the, and then we click OK. Sorry. Then it shows us whether the residue, the distribution of the residue. Okay, now this one, the normal test. Couldn't find it. So go. Explore. Okay, probably we'll just move on. Sorry. Then we also have another assumption for the residues, which is the constant variance. That means all the variance of the error term should be equal one fixed value. However, in reality, most of the error term or residues, they are heteroscedasticity. That means the variance vary depend on the number of error terms we choose. Okay, maybe if we choose the first 10 error terms, the variance is 2, and if we choose the second 10 error terms, then the variance may be 3. So in that case, we call the error terms or the estimation is a heteroscedasticity. And that will also cause the unreliable of the statistics results for the coefficients and the model. And to check out whether there is arbitrary say density in the error terms. Also, we use the histogram pictures, or we scatter plot the error terms and the dependent variable, or the estimated dependent variable, and to see whether they are normal distribution or whether they have a certain relationship. And then we can do this in simply visualized in the SPSS, where we go regression, linear, and then we can plot. We can click on the plot, and then we choose the standard residue. The standard unstandard predicted value to y, and the unstandard residue to x, and we click on the histogram, and then we run the regression again. Then here we can find out the histogram and also the scatter plot. And in this case, we can see this is pretty skewed to the left side, and that is not the it is not a normal distribution. Then we can suspect, or we will induce that the variance of the error terms is not constant. And then that's pretty much what we do for estimate the model, and how we validate the model. And we run this process time and time again, until we generate the best model with the best statistic or best test results. And on top of the simple linear regression model, the most likely the model we will use for our project is the multilinear regression model. However, because in that case we will have several variables or several independent variables in our model. In that case, we have to think about another thing is multicollinearity. So that means there is a linear relationship between two or more independent variables. So, for example, in this case, if on top of bedroom, if we also want to include the distance into the model, so I'm not sure, maybe the bedroom also has a linear regression or linear relationship with the distance. So if in that case, we can run the model first, and if we see there is very high R value or very high R square value, however, all the coefficients are not significant, or we have a very high simple correlation coefficients, where we just estimate them pairwise, then we will see probably there is a multicollinearity in between the independent variable. And also we can use the high variance inflation factors to test whether there is any linear relationship between the independent variables. So what we do is that we go to the SPSS skin, and then we go analyze. I think the one is the regression. Is that regression? Linear. And we go to analyze linear regression, and in the statistic, we untick the estimate or untick other box, but the collinearity diagnosis, and then we choose the variable where we want to see whether the bedroom. Oh, sorry, we should move the transaction first. Well, we want to see whether the bedroom has any linear relationship with the distance. Then we click again, and then it shows us the value of the variance inflation factor. And if the value is more than 5, then there is a linear relationship between the variables. And if it's less than 5, there is no. So in this case, the bedroom has no linear relationship with the distance. Okay, so and then after that, so if there is one, how can we do this? One is we do nothing, right? And then probably we can drop one or more independent variables in our model. Or maybe we can find more data, and also we can transform the linear regression, the two variables into one, based on the linear relationship between them, and then put the combination or put the new variables into the model. And another case for our regression is the dummy variable. And normally we can use the dummy variable to indicate an event or to indicate an existence of one condition. For example, in the hedonic model, maybe we can use the dummy variable to indicate the existence of fireplace. So it's like we define 1 if there is one fireplace, and 0 there is no fireplace. And also in the time series, also we can use the dummy variable to indicate the occurrence of certain events or certain, for example, like say the time series data is like if it is equals 1 when there is during the global financial crisis period, and 0 during if not in the financial crisis theory, or it is one when the GST being introduced to the system, and equals 0 when GST had not been introduced to the system. Okay, so that's, and then we can use the double variable into our regression. And I mean in SPSS, I mean that's the same procedure. We run the regression model. And there's another one which I want to highlight a little bit, is the natural log linear regression. So because I mean the previous linear regression model is like we assume that the house price has a linear relationship with the factors. However, maybe in the reality, it is not in that case. I mean, for example, probably the house price should be expressed or specified in this format, and rather than the linear coefficient, it's more like the shows the power of the corresponding factors, or the elasticity of the corresponding factors. So in that case, we can transform all the value into the natural log value. So in that case, we calculate the natural log value of the left-hand side and the right-hand side, and then the left-hand side becomes to ln p, and then the right-hand side becomes the linear relationship of the natural log value. And here, in this case, all the betas, all the coefficients, it indicates the elasticity for the number of bedroom against the house price. So that's the elasticity. I think we talked the elasticity before in the previous lecture. That indicates the proportion changes. So that's so how much percentage changes in the house price be influenced by the proportion changes in the number of bedrooms. So I mean that's the elasticity, not the real term. I think that's all for today's lecture, and then in the following tutorials, maybe we can do some practice by using the SPSS. And if you have any questions, you can ask me or Niraj. Okay, thank you very much. sorry, what's your topic? I don't. Uh-huh. In where?
In Port Phillip.
Okay, yeah.
And then also at the distance to the coastline, the coastal line.
Yep. Oh yeah. Now I recall your topic. Because the only that's okay. I mean, the only problem is that how do you define the coastal line? Short is yeah.
I think the fronting will be outside.
Super curious about the protest in Hong Kong. It's like I'm sure everyone is asking me.
Yes, I think in the assignment to you didn't you just show the data when the data is collected. You'll see what exactly you are going to. Yes, to do.
Yeah, I'm following it. Yeah, for her to step down, can really have a picture.
Okay, that's great.
People are just trying to get it's getting crazy like
Yeah, I think that is a problem. I have no idea how to. That's why I asked you how you can solve that. Because the copyright have a special kind of movement.
That's like a stick.
Yeah, the short distance.
But the police officer off duty is a citizen as well. So that's
because it's not like a train station. Right? The train station, I mean, one station only has one pair of.
I have friends that are working
one
expats, but like it's affecting business as well.
Yeah.
The tourism. Like it's like a big cycle, so one affects the other.
For your cost of life, and also you should the scope of the cost of life. So for example, 2 kilometers long, and from where
I saw the videos of that, like meeting people up on the train. Oh yeah, press Happy Square.
we can also create
Try to find.
yeah, just a club. I mean, that's a big point. However, just I don't know whether but yeah, by the data, I mean, alright, because we are right, is there any information higher or maybe famous view? Yes, and then all the and then we can find several landmarks along the
It's already getting crazy.
yeah. Yeah. Something like that. So then you have the identify the lab species.
So you think it's gonna
specific date for the semester, and you said we need to handle it maybe now or after the break.
okay?
Week 11, sorry, it's week 7, right?
This
Week 7, week 9, yeah.
week 9,
Yeah.
week 9 Friday.
Yeah.
But because the guide was an option that shows that maybe after the break that you do that, so there are little difference.
Oh, really?
Yeah.
Or maybe after. Maybe after.
So about the semester is more like
Of that. Yeah. Statistics. Yeah, statistics. Maybe, I mean, probably you will use a little proportion of the following week's lecture. But not the regression part. Not the regression part, just basically the statistics, the descriptive statistics, or maybe some test like as I mentioned, correlations. Yeah, maybe correlation metrics, or maybe if for the service, maybe like some unit root test, or maybe for the cross-sectional, we see the linearity, something like that. So very central.
if I got 2 data sets that I can contact both
You don't.
What do you mean by two
because the question that I'm looking at eventually is the
Go away for like for half a year.
property because the data set for facility and property. So I got 2 data.
Will eventually go away.
So why are you going to analyze two data sets? I don't. So it's like the property bias and the property.
It's like
Is the same? Are they the same? I mean the value is
one is the sports facility distribution,
the location.
and another is the property transaction business. So I
Property what?
transaction
Oh yeah.
so I did. So
No. Now you should. I mean, by assignment 3, you should combine. You should only have one data set for your project.
yeah, well,
So you see data set 2 is like you collect the data set from 2 resources, right? Then you have to merge them together or integrate them together for your project. So that's what we want to see in assignment 3. Is that you are not going to describe based on the original data. It's something maybe you work on.
and also it's more like comply with the workflow that we put on the poster.
Yes.
How we do it.
Yes. The next step after.
Do not like to work out a result on chemical research.
No. I mean, yeah, it's up to you. Because I mean, there is no inventory results, right? Because the regression is a loop. Right?
Oh, yeah.
So it's like
It's always addressed.
Yes. Okay.
What's the meaning of this?
The critical value, right?
The critical value, yes. So normally it's around 4.
Oh yes. So
Is there a table to
Yes.
for comparison?
yes. I mean, because I mentioned that there is a table called F distribution.
Yes, distribution.
Yes.
So
T.
this one is yeah, just want to know
How to find out the
how to
critical
compare
value?
the result to the
yeah.
to that table is to see the
So the table it indicates all the values at different test probably distribution table.
Sorry.
What they call 分布表，
支撑度这个表，
是叫分布表吗 ？F
I mean,
对对
yeah,
对。
yeah, this is so how to say this or how to use this?
Yeah.
So it is for example, this example that
So it's like now you
between the two
because
numbers.
no yeah because now you have to change you have to choose the freedom, the degree of freedom. Where is that? This one, that's key, and this one, and minus k minus one.
Yeah.
So in this case, maybe k is like 1, right? And n minus 1 is 200 something. Yeah.
K is 1.
I think k is 1. And then we see it's a 2, sorry. And yeah, then we just choose this one, and then down to the 200 something, which is here is unlimited.
So we just see this code.
Yeah. So this one,
So this one is K.
This
so
is
if
K.
I use if the K I use as 2, so I just see this code
Yes.
to find the answer.
Yes, so to find out which is located. For example, that's the 95%.
Yeah, 95%.
Yeah, so that's then we probably go to this unlimited, which
Unlimited.
is 3.
Yes.
Yeah.
So
Here
is a 4.32.
Yeah. So normally, yes, here you probably is 3. If your value is bigger than 3, then we reject the sorry, if it's
So if the value is 4.32,
yes, we reject the non-hypothesis.
So I mean the
No, that's the value of FC.
sorry.
That's the value of FC.
Okay.
So this
Also,
value.
this is FC. This is the table.
Yeah, that's
this
the
is
critical.
value.
That's where FC is a critical value.
Okay.
That's you check from the table. You find out from the table.
I just find this number in this table.
Yeah, and then you compare the calculated F against the number you found in the table. So if the calculated
So this is the number in the table.
yes,
I mean, so,
yes.
I just
correct.
can't find the 4.32 in this table, so I just feel a little.
Yeah.
Yes,
Because I'm not quite sure. Because
So just give a similar number, or we use a different table. I don't know how to find this.
I don't think that's a.
That's not a standard.
I'm not sure. I don't know why the table shows this values. Because based on my knowledge, it's not 1, 2, 6. Yeah, I forgot where I should choose. However, I mean that's the way how we select the
Yes.
critical value. But I'm just assuming that maybe this is just for. Did I find this? Yeah.
Yeah, just find website.
I
don't
found
know whether
the
it is
same.
right.
Yeah, cause I found the same way. But anyway, that's
Yeah,
just
but-
the
Anyway,
critical value of the F.
So the F is so the F you calculated is
Based on
between
this.
the 4.32.
No, it's like
means-
while you do the test, you have a preset critical level. So it's like yeah. So that it's like the level you choose. For example, you will